In this video, we're going to talk about solids. Now, solids have definite volume and definite shape, but we're going to explore different types of solids and what they consist of and some of their properties. So here is a table that lists the different types of solids that we're going to discuss in this class. All right, and so the different types of solids are, you have ionic solids, molecular solids, covalent network metals or alloys, and then lastly amorphous. All right, and so let's start with the ionic solids. So now ionic solids consist of ions. Okay, so when we talk about ions, remember charged particles, and it's particularly an ionic compound. So like, for example, like NaCl or calcium carbonate, which they're broken up into its respective ions. So metal with a non-metal kind of bonded together. Okay, so these are the smallest units, and the forces between them, as I said, is between a positive and negative ion. So it's between a cation and an anion. Okay, so what are some of the properties? Well, typically ionic compounds, they're brittle, they're hard. So if you think about table salt, right? Table salt, especially if you have it clumped up together, it's hard, it's brittle. You could break them up into pieces. They have a very high melting point, and they follow a crystalline structure. So it simply means that there is a pattern in which the ions are formed. All right, and they're formed in a very particular pattern. So like, for example, if we're talking about sodium chloride, right, the pattern in which the ions are formed in are like Na plus Cl minus, Na plus Cl minus, Cl minus, Na plus. So this is exactly the structure of sodium chloride. All right, and so when you have this organized structure, we call it a crystalline structure. Okay, all right, and then so here are some examples. Once again, you have sodium chloride. Oops, I want to use the highlighter. Sodium chloride, potassium iodide, calcium phosphate. All right, so these are all ionic compounds, and these will all have these type of properties, and we call them, once again, ionic solids. Now let's look at molecular solids. Molecular solids are made up of molecules. So particularly we're talking about covalent compounds, really. All right, covalent compounds. Remember, covalent compounds consist of two or more nonmetals, specifically. All right, and so the forces that keeps these type of solids together is intermolecular forces, specifically. All right, and so just to remind us of the intermolecular forces that we talked about is like hydrogen bonding or dipole, and lastly, London dispersion forces. So these are the forces that keeps these molecules together in a form of a solid. Okay, all right, so what are some of the properties? Well, the properties, they typically are softer. All right, they have low to moderate melting points, and the reason why they have low to moderate melting points is that what's keeping them bonded together are intermolecular forces. All right, now intermolecular forces compared to intramolecular forces. Intramolecular forces are forces within a molecule, while intermolecular forces are forces between molecules. Intermolecular forces are much weaker than intramolecular forces, and so that's why for molecular solids, they have much lower melting points, because it doesn't take much energy to break intermolecular forces, versus like ionic solids. If you're trying to get them to melt, they're bonded together by intramolecular forces. So intramolecular forces are much stronger, so you need a lot more energy. The temperature must be higher. All right, and there's some examples of solids, of molecular solids. You have ice. So water is bonded to each other by hydrogen bonding, which is an intermolecular force, right? Wax, they're bonded together, but mostly London dispersion force, some dipole. Frozen carbon dioxide, all right? So together by CO2 are locked together by London dispersion forces, all right? And all solid organic compounds. Now, if it's a solid organic compounds, they're locked together. These molecules are bonded together by intermolecular forces. And particularly if it's organic, it's somewhere is either, you can have London dispersion force, dipole, and depending on the organic compound, it could also be hydrogen bonding, all right? And so all in all, it's intermolecular forces that's keeping them together. Okay. All right. Now, the next type of solid that we're going to talk about is covalent network. All right. Now, covalent networks are typically atoms. All right. They are bonded together. And how they're bonded together through covalent bonds. All right. Oh. Wrong thing. All right, by covalent bonds. So, in other words, they're bonded together by intramolecular forces. All right. Now, as we said, intramolecular forces are forces within a molecule. All right. And so, this is the reason why that the properties of these type of solids are they're very hard. They have very, very high melting points. All right. And they have a very crystalline structure. Okay. Because you're trying to overcome an intramolecular force. All right. Covalent bonds as an intramolecular force. And so examples, diamonds. All right. So diamonds are basically carbons, chains of carbons locked together by these intramolecular forces. Intramolecular forces, these covalent bonds. And so this is the reason why carbon it's one of the toughest substances on Earth. All right. Quartz, so such as silicon dioxide, tungsten carbide. All right. So all these are bonded together by covalent bonds. All right. Which makes this covalent network. All right. Now the next one that we're going to talk about is metals or alloys. All right, and they're made up of metal atoms specifically. Now these metal alloys, these atoms, are bonded together in which a system that we call metallic bonding. All right, and the metallic bonding is an attraction between metal ions and the surrounding mobile electrons. So what does this mean? How does that look like? All right, so I'm gonna kind of draw this out for you. So if we took a sample of a metal, right, and we were to kind of, go into a microscope, what we will find that the nucleus of the metals, all right, so here's your nucleus of the metals, they're arranged in this orderly fashion. Now, metals particularly have low ionization energy. All right, what does that mean is that the nucleus doesn't have as much as a good grasp on the valence electrons or the electrons themselves. And so what's going to happen is that these electrons are able to flow pretty much freely through the substance, through the metals. So you have these electrons, which I'm going to notate as these negative red dashes, all right, are able to kind of move around freely in between the nucleus of these metals. Now, you also have to remember these nuclei, but these nuclei are positively charged, all right? And so we have these positively charged nuclei that are organized orderly, all right? And then you have these electrons that are able to flow freely through this matrix of these positively charged metal nuclei, okay? And so that's what this means. And this right here is this is what we call metal bonding, all right, or metallic bonding, because you have these electrons that attract essentially these positive nuclei, all right, in such a way. But the ionization energies of these metal ions are still so weak, these electrons still are able to flow through. So they're moving, and it's moving at random, okay? Now, what allows metal to conduct electricity? So what does it mean for something to conduct electricity? Able to conduct electricity is when you have a current. Now, a current is basically when you have charged particles that are moving a very specific direction. Okay, and so what allows metals to conduct electricity is that the fact that these electrons are free moving, all right? And if you could get it moving one specific direction, then you could have that substance able to conduct electricity. So for example, if you could get all the electrons to move this way, you have yourself a current, and thus it will conduct electricity, all right? Because all the charged particles are moving a very specific direction, okay? Now, what are some of the physical properties? Metals, they tend to be lustrous or shiny, soft to hard, kind of depends on the substance itself, right? So like sodium is a very soft metal, titanium is a very hard metal. High melting points, all right, because there's a strong attraction. It's a Coulombic attraction between the positive charged nuclei and the electrons, all right? So you have to actually, give it a lot of energy to break that attraction, make it a lot more free flowing for that substance to become a liquid state. And then you have this orderly crystalline structure, okay? Now, some examples of metals and alloys. So metal elements such as iron, copper, tin. Alloys. Alloys is just a mixture of metals. So like bronze, steel. These are just some of the examples, okay? Now, last but not least, we have amorphous solids. Now, amorphous solids could be made up of atoms, ions, or molecules. It just really kind of depends, right? And it could be any type of interparticle structures or interparticle forces that are within amorphous solids. Now, what does an amorphous solid looks like? What are some of its properties? Well, it's non-crystalline. That means that the atoms or the molecules that make it up are not in any type of organized order or fashion, okay? There's no sharp melting point. That means it kind of fluctuates, depends on the substance itself. It has the ability to flow, all right? So it's very, very, very viscous, all right? And so they could be also carved into edged when it shatters, all right? And so here's some examples, some plastics, tar, glasses, all right? And so these are amorphous solids, all right? And so these are just the examples of the different types of solids that you have to know, all right? Looking at the smallest unit, the interparticle forces, and some of the properties of each of these type of solids.